Thank you. Thank you for coming back after lunch. I know the pool looked very inviting, although there was also a lot of food, so you can digest and hopefully not nap until 8 p.m. or something at dinner time. So I'm in a contrast to this morning where we heard really great theoretical talks. I'm kicking off the experimental afternoon. The topic is topological electronic devices, which I think has been, today I'm talking about topological electronic devices, and tomorrow I'll talk about topological magnetic devices. And I chose to talk about devices because I think that there's an opportunity here to think beyond the underlying physics and a little bit more about what we can actually measure experimentally and what we can possibly do with these for various reasons. Also, from my own personal selfish perspective, I'm about to take over an engineering school, and I thought I needed to have some engineering bona fides. So, devices you get. Let me first acknowledge my collaborators here, and these are my students and postdocs. You can barely see this, but they're there, who worked on this. I've had a great theory collaborator in Matthew Gilbert, who's in electrical engineering at University of Illinois, and materials growers as well. Okay, so why do we care about devices? I mean, should be obvious why we care about devices, but for one, I think we care about doing interesting physics, but it's nice if we can do interesting physics and also have some impact. I know the recent controversy about LK99 is, a controversy. It wasn't correct. On the other hand, you can see how excited people get, including among the physics community, by thinking about something that we actually think about could have some application. And so I think it's worthwhile sometimes to take a step back and think about what we are doing could actually be impactful in the broader society, or even if it's not ever going to be impactful, what would it take for it to do that? It sometimes helps us sharpen the sort of questions we ask. And of course we always, at least I do, and I know many of the faculty here, when we write funding applications, we'll start them saying, dissipationless quantum, topological devices may solve the energy crisis and the climate, right? So, okay, we write that, but, again, it's worthwhile sometimes stepping back and saying, okay, how good are these as FETs or interconnects or something else like that? Is that really possible? Do we care about it? What else can we do with these? And then, like I mentioned, it also just helps us think about it. I think, when I tell my family what I do, they ask why I choose the materials I do. Okay, they don't really ask it. I tell them why I choose the materials, and I say because either they have to have interesting physics associated with them, or they should have some possibility of being useful. And so I think these two things often drive us toward, of the many materials we continue to focus on that become faddish in the field, they're usually one or the other, and sometimes both. So in this talk, I'm going to focus only on topological insulators. There's many other types of topological materials. We happen to study topological insulators. They're very nice for doing transport on, especially because you can see some of the topological properties in transport. They have a band gap, which makes them, we talk about electronic devices. It's really nice to be able to control the conductance via a gap. So these are gapped materials on the whole. They have surface states, again, that are experimentally accessible, lack of backscattering, those, climate-changing dissipationless states that we promise are in there, plus really interesting physics that is also possibly useful for devices like magnetoelectric effects, spin orbit, spin momentum locking, and the materials, there's a lot of different materials we can choose from in these. So, what devices do I mean? And here I'm really thinking about electronic devices as things that we just want to control the flow of electrons one way or another. And actually, that's electronic. We'll talk about magnetic devices tomorrow, but I've just listed some of these. We can talk about field effect transistors, interconnects, junctions, qubit-type devices, magnetic devices. I've thrown in emergent quantum states because even though these aren't devices, this is the physics I'll talk a little bit more about, but even though they're not devices, we do think about what sort of states can be tuned or used for different applications. Why do we care about turning on and off edge states, for example? What can we do with that? And I also want to mention that when we talk about devices, there are materials requirements. Why don't we see graphene in all sorts of computers and things? It's because at the end of the day, we're really limited by materials properties and materials constraints. So things like in topological insulators, we want to make sure the surface states dominate. And we need tunability. We have to have some knob where we can turn things on and off. And we also need generally to have lowest order clean interfaces and other material properties, and also just make these things at scale. So this is just good to keep in mind as we talk about devices and even the physics, that these are properties that are requirements to even start thinking about devices. Okay, so today I'll start by just talking about device fabrication, tunability, and achieving the surface state regime. I'll actually spend some time on this because that's the basic necessity in order to get to using these and understanding these sort of materials. I'll then mention just in one slide what possibilities there are for things like interconnects and FETs, talk about Josephson junctions, a little bit about emergent phenomena, and then tomorrow I'll talk about magnetic devices because that's its own big area. And as I mentioned, the goal today is just to understand the promise and limitations of these devices, give a little bit of an overview and see what they're potentially useful for, and also just clarify what sort of experimental signals, challenges, and opportunities there are for transport in these systems. And again, I focus on transport because when we talk about devices, they're generally transport devices, right? We don't carry around mini ARPUSes to run our computers. So, even if you see a band gap or band crossing in ARPUS, unless you can measure it and utilize it experimentally, it's not going to be super useful for devices. And these are some of the references I'll talk about today. Okay, so 3D topological systems. Again, I'm talking about 3D systems which have surface states. They have strong spin-orbit coupling, like I mentioned. They should have strong insulating bulks and spin momentum locked conducting surface states. In topological materials, there's a ton of topological materials which have been discovered. This is one of the great things about studying these materials. There's many, many different options with many different material properties. For the 3D topological insulators, there's a whole bunch of layered chalcogenides. You can see very similar structures among these. And then there's the magnetically doped ones, and down here we have other weak 3D topological insulators and condo insulators, and here. So the topological insulators I'll mention are in the dark blue here. But there's many other materials that can be played with. Now, we focus on bismuth selenide. This was the first topological insulator, I think, one of the first ones measured. It's still the best example, partly because it's just so accessible to experimentalists. You can see here that it has a really nice band gap of 0.3 eV. That's big enough that you can actually measure and use for different purposes. You can see clearly the Dirac surface band structure here with these topologically protected states. This map was taken at room temperature, which means that all of these states exist at room temperature. And that's also really important because if you want to think about or use or even measure these, it's nice to not always have to go down to very low temperatures. And the spin momentum locking states have been determined by spin resolved ARPUS as well. So many of these properties have been experimentally determined. Now, one of the issues in studying these materials, of course, is that what we want to do most of the time is tune in and out of the topological regime, which would be, ideally somewhere right around the band crossing would be the Fermi energy, and then we just tune up and down and never deal with the bulk bands at all. It turns out for almost all of these materials, unfortunately, the Fermi energy isn't at the Dirac point, but rather somewhere in the bulk due to just vacancies in the system. So most of the times when you want to measure these, you have a metal and not an insulator. And this is a problem because most of the time we want to study the surface states, which have all these interesting properties, but we can't access them because you have a surface state, which is a nice conductor, but then a bulk, which is also a really nice conductor. And so you can't differentiate between the bulk states and the surface states through transport alone. And that's a problem when trying to study these. Generally, like I said, almost all 3D TIs have this problem of vacancies leading to bulk metallic states. And so it's a really big issue of how do we actually attain the surface state regime in these cases. There are many different solutions for getting there. You can do gating, top gating and back gating. That's pretty effective. Sometimes using a back gate alone isn't strong enough to tune you into the Fermi energy into the Dirac point. There's a lot of doping that you can do, especially things like BSTS or BST. That's selenium doping on bismuth selenide, antimony doping on bismuth selenide, and tellurium doping. These are effective, but sometimes introduce disorder. There's chemical doping, which is I'll talk about. This is a nice technique. It's a little hard to control. Yes?
Sorry, why can't you, you have only one surface state of many, many bond states, right? Shouldn't the density of states much higher? And it's just metal and not topological? So why can't you distinguish them with transport?
Are you asking if the surface state has a higher density of states than the... Yeah, but there's a lot more of it, right? So there's many electrons in the bulk.
Yeah,
There's a lot more electrons in the bulk than there are in the surface. So even if the surface isn't as good a conductor, right, just by looking at, we're looking at resistance, not resistivity. And so if you're just measuring end-to-end transport, if you have a bulk to the thing, right, you have a surface state that's well conducting, but then a lot of bulk that's maybe not as well conducting, but when you measure resistance or conductance, it contributes more to the conductance. It's just a parallel resistor that's thicker. Is that, yeah. So you have a thick, not as good resistor, but parallel to a thin, highly conducting one. But overall, even if their resistivity is lower, their overall resistance is going to be higher in the surface state than the bulk state generally. Okay. Yeah. I mean, this is true for all of these systems. Once you get up into the bulk regime, it'd be like trying to measure an edge state on a metal. It's just, you see the metallic states, not the edge states, unless there are very specific properties you can find. And please do interrupt me with questions. You can also make heterostructures of these systems, like bismuth solenoid on top of bismuth telluride, which is also very effective, although sometimes this does change the properties of the system as well. And just to mention, there are other materials, the non-chalcogenides, like samarium hexaboride. This does have a Fermi energy at the Dirac point, but it's a Kondo insulator and it has some relatively complicated bulk behavior. And so this has been somewhat difficult to understand some of its behavior, such as its quantum oscillations. So when we try to approach a Dirac point in these systems, we take a combined approach of basically 2 or 3 of the things I just mentioned to really try to get to the surface state only regime. We start with a thin flake of the material, and as was asked, why do we deal with a thin flake? Because we have less bulk in a thin flake. So we'll deal with something that's maybe 20 nanometers thick, where we hope the surface contributes at least as much as the bulk in a thin enough system. We then take the material we use has antimony compensating for selenium vacancies, and then which also brings down the Fermi energy. We put contacts on it, and then we'll often use what's called chemical doping, which is just a chemical material that has a strong affinity for electrons, and so it basically sucks a lot of electrons off the surface. Because it's sitting right on the surface, it can be more effective than an electrostatic gate. And then it just locks its doping in as you go to lower temperatures. And so it's a very effective way of lowering the Fermi energy in these systems. And then on top of that, we finally use a electrostatic gate, a back gate, or a top gate to be able to tune the Fermi energy all the way through the Dirac point in these systems. And so this allows us to not just access the topological region, but tune all the way through the topological region to distinguish between topological and non-topological behavior in transport in these sort of materials. So this is the sort of transport data we see. This is resistance, the function of the back gate for a flake of bismuth solenoid, you can see here, which has chemical doping on it and a back gate. And you can see as a function of the gate, we can now access the Dirac point. And if you measure Hall measurements, you can see where it changes sign. So we can clearly gate all the way through the Dirac point in these systems. And then we can now differentiate between where the bottom of the bulk conduction band is and where the topological region is to really differentiate behavior. Yes?
Are you not worried about gating the 2 surfaces differently of the TI?
Yeah. So we that's right. So we try to use very thin ones. So we found that if they're less than about 20 nanometers, you can evenly gate the top and the bottom. And this is a study that actually was done in a Maryland group a while ago, showing that if it's thinner than about 20 nanometers, you can basically gate them both together. As it gets thicker, you have to use both a top and a bottom gate. But if you use a top and a bottom gate, you can avoid that. But in our case, it's thin enough. Yeah.
Does that only work then if you have a strong topological insulator? I mean, sometimes it depends on the termination, right? Do you only use just the gate then?
Give me an example of what material you think it wouldn't work on in this case.
Do you have like a weak topological insulator that like will only on some of the stuff that have substrate, right? So it just depends on how you do it.
So in this case, we assume that we have surface states on the top and the bottom. Is that your question here? And I'll show you that we think we do have surface states on both the top and the bottom in this case. No, we don't need it. That's right. So it's a thin enough system that we ignore the sides. Yeah. Yeah.
Have you, like with this chemical doping, have you ever observed that you shift the direct node up and down in energy compared to the surface? Because the direct node is not really fixed by anything. Right? Like
Yeah.
Push it into the bulk, then.
Yeah. So we haven't done ARPUS on a chemically doped system. So we don't know exactly where it is in. So, and in fact, the only way, when I say I know where the bottom of the bulk conduction band, this is from comparing the ARPUS of an undoped system to the ARPUS of this system, and then assuming that the bottom of the bulk conduction band is around the same place. Yeah, so we haven't, that would require actually doing ARPUS on it. So yeah, so we have to see where, yeah, to get this value, we have to compare, right? Otherwise you wouldn't know where it is. We have to actually compare ARPUS to this. And to do ARPUS on a flake like this would be harder. Yeah. Yeah, so these are relative positions. Yes. Oh, sorry. I don't think that's been done. I don't know. Does anyone, Fawn would know. Has anyone done ARPUS on an exfoliated flake?
No.
Does he do it on exfoliated flakes or not?
Exfoliated
Inside his chamber, in situ. Yeah. Yeah. Was that your? So yes. But you require. I mean, it's not everyone can do this, right? So a few people do it, but it's not that easy to do it. It's certainly not easy to. I mean, we have to do transport. You want to put contacts on it, and so you wouldn't do it on the same system, nor would you want to chemically dope inside the ARPUS, if that was your question. Yeah. Was there a question in the back? Yeah.
Do you see on the thinner plates maybe some kind of hybridization between the top and the bottom layer?
Hybridization, you said. If we make them less than about 8 nanometers. Right, so we always try to go above. So our goal is to go above 12 nanometers, so we don't get hybridization. We don't want to be close to that, and below 20 nanometers, so that we can gate them uniquely. So it does require some fine tuning because we use exfoliated flakes, and I'll say why later. But we find that we just get cleaner surfaces doing this way, and there's also some issues in the MBE grown ones with just hybridization at the interface with the substrate that we want to avoid, and so. We like using exfoliated flakes, but there's a small range you have to work really hard to get in that case. Yeah.
How many couple layers would that be for that thickness you just said?
What is it? About 5 or 6? It's like 4 nanometers per quintuple layer or something. All right? Something like that. Yeah. Okay. So at least we can estimate where we are in the topological regime. And as was mentioned, we're comparing this to ARPUS. So when I say, we're exactly at 20 volts, you should consider this just a region. So what we consider is if we're out here somewhere, we're in the bulk region. If we're very close to around here, we're almost certainly in the topological region without being really exact about it, which is hard to do without doing ARPUS in situ for the doped system. Okay, so we fabricate these things. In this case, I'll talk a little bit about some experiments we've done on a nanowire of these. Again, this is just an exfoliated nanowire. We exfoliate, we stick it on the substrate, and we look for wires that look like this. The advantage there is we get really nice edges as opposed to etching it ourselves. So we find wires that look like this. Again, the thickness is about 15 nanometers, right in our sweet spot, and the length and the width are a couple hundred nanometers each. We contact it, put doping on it, and then have the substrate act as a backgate that allows us to tune through the Dirac point. And then we measure conductance on here. You can see we get really nice conductance that gets us through the Dirac point, and also relatively high conductance for this sort of system. And this is something that's, if you've worked with graphene, I don't know if I've worked on graphene, but if you look at graphene nanowires, as you make them to the scale of 100 or 200 nanometers, the resistance increases tremendously. And so already with these topological materials, you can see that even when you make it really pretty narrow, about 100 nanometers, the conductance stays around E squared on H, which is relatively high. So there's somehow just less edge and boundary scattering in these systems than you get with other sort of comparable systems.
These fluctuations on the curve, are they actual?
I think, yeah, those are UCF. Those are, yeah. So these fluctuations are reproducible here. Yeah, that's the problem with measuring a small system. That's right. Okay. Great. So So before I talk about devices, we have to know, I've tried to say that we're in the topological regime. We think we're measuring the surface state. So what are the unique, how do we know that we have these properties of the surface state? And some of you asked questions about this already. How do we know that we have top and bottom surfaces? How do we know that we're even surface state dominated as opposed to seeing the Dirac point? So for this, we have to actually do some measurements, which I'll say a little bit about. I just wanted to mention, it fits in with, I don't need to say anything about this because you heard all about these already, and we have some of the world's experts here, but one of the great ways of looking to see that you have surface states is to see if you have quantum oscillations, which should change as a function of angle of magnetic field. So as magnetic field is rotated out of plane versus in plane, you can see 2D oscillations and prove that you have a 2D system that way. You can also do STM. This isn't transport, but it's a way of actually showing that you have things like lack of backscattering on the surface. I'll mention a little bit more about one of the experiments we did to determine some of the surface properties, which is looking at Aronoff-Bohm oscillations in this sort of nanowire surface states. So to see Aronoff-Bohm oscillations, we want to start with a nanowire, and you want to start with a nanowire that's narrow enough that you can see 1D subbands, and so your conductance should be quantized into these 1D subbands. And if you have a hollow wire, right, then the electrons should traverse the circumference of the wire. There shouldn't be a bulk. If your surface state dominated, right, if the bulk is insulating and the surface state is dominating, then the electron should go around the surface state. Now, if you apply a magnetic field through a hollow wire, you accumulate a phase, right? That's just your Aronoff-Bohm phase. And this phase will cause the conductance to oscillate as a function of H over E. Okay? Now, there's some conditions here. You have to have something small enough that you get quantization. So in our case, we have a very small area. It's only, like I said, a 15 nanometer thick wire. That's 100 by 150 nanometers. We have a small area. We expect to see a flux period of oscillation around 2.5 Tesla, which is accessible. You also have to have a well-defined path around the circumference. So if the top, we're applying a flux through a 3D material, which should be, it actually has stuff in the middle, which is the business solenoid. So, this should easily differentiate between whether your conductance is around your surface states, where you have a well-defined path, or whether it's through the middle, where you have many paths that will average out to zero. Okay. You also require phase coherence. This is another property that you should have. If you have lack of backscattering, you should have a pretty clean system that's phase coherent. To see these oscillations, you need phase coherence, and you need ballistic or quasi-ballistic transport. Again, without ballistic transport, you'll get other sorts of oscillations that are associated with disorder, as opposed to H over E oscillations. Okay. The other interesting thing about the topological materials is that they have this extra phase of pi, and so what this does is it leads to a gap in the first subband that, if you add a magnetic flux, will cause that first topological subband to reappear. And so in a topological insulator nanowire, you expect the conductance at the Dirac point to oscillate with a period of H over E and have a maximum at half a flux quantum and a minimum at zero, which is unlike what you'd expect in other materials because you have this extra phase of pi. And then finally, because we're tuning as a function of magnetic field, we're gapping out this topological mode. You expect to start out with, as you apply fields, with a gapped mode and end up, of course, I said, with the mode that's present as you apply half a flux quantum. So if you take conductance, you measure conductance as a function of applied field, you should see something that goes from a minimum at zero, right, to a maximum at half a flux quantum. But then as you take another cut that cuts through different bands, you should see that oscillate. You should go to a max at zero to a minimum as you start splitting those bands, and then that alternates again. So you should also expect to see phase alternation. This is just a function of seeing 1D subbands in this system, which is also something that would be interesting. Okay, so to cut to the chase, we measure conductance. We see these Aronoff-Bohm oscillations. They have amplitudes that are close to E squared over H. They're very clearly H over E oscillations, and as I mentioned, you can take a Fourier transform, see they're H over E, not H over 2E, which would be a disordered case of oscillations. And overall, just from seeing this alone, right? Again, this is a really, if you see Aronoff-Bohm, if you tried to measure Aronoff-Bohm oscillations in just a strip of metal, you would see almost nothing, or you'd see nothing. Okay? And you'd see nothing because you don't have a well-defined phase coherent path around this. And when I talk about, phi over phi naught, this phi naught is determined by the area around the circumference of the nanowire. And so the fact that we have conductance oscillations as a function of phi over phi naught defined by the area of a hollow nanowire tells us that our conductance is in fact around the outside of the wire, not the inside. And so it's telling us that one, we have this high conductance, which is consistent with theoretical expectations, but also this is a clear signature of surface states. And what's nice about it, too, is that you can see that because we have to have a path in the top and bottom surfaces, it means that we have somehow coherent states, surface states, on the bottom surface as well as the top surface. And again, experimentally, this isn't totally obvious, because if you put a topological material just on a surface where it's now interacting with the surface, do you still have a surface state on the bottom? Right? Theoretically, you do, but experimentally, that's not really known unless you measure something like this. We also see, if we measure this, the function of gate voltage without going through the details, you can see if you look at 0, you can see the alternation of the phase. It goes from a dip to a peak, to a dip, to a peak, to a dip, to a peak. And this maximum and minimum alternation is due to passing through 1D subbands. Now, I'm not saying that we hit every 1D subband with our gate voltage, because I think we probably get a couple at a time, but the fact that we see this phase alternation tells us that we are indeed in a regime where we can access 1D subbands, which is, again, interesting, as I'll show later, for different sorts of applications involving topological materials. Okay. And we also always observe a minimum near the Dirac point, which is what's expected theoretically from the topological regime. Yes?
One question. I didn't get how you go above in the vertical axis, how you make measurements that you go above the axis.
Oh, sorry. These are, sorry, the separation here?
Yes.
Oh, those, I'm trying to remember. The conductance increases, but these are artificially separated. Actually, they're not uniformly spaced. Is that? Yeah, I'm sorry about that. Yeah, yeah. Then why is our conductance so high? You mean? Or?
I just found how do you recognize that these are from different layers?
Oh, you mean the alternating conduct? Oh, okay. Yeah, I understand that. Yeah, I went through that pretty quickly. I feel like this is losing battery. So as a function of magnetic field, if you start with doubly degenerate bands that are gapped due to the additional phase at 0 flux, when we measure conductance, we're basically as a function of gate voltage, right? So let's say we start at the Dirac point, and we have this green line going from the Dirac point, and we increase as a function of magnetic field. So at the Dirac point, at 0 field, we should have 0 conductance, right? And then as we get to the Dirac point at half a flux quantum, we should have h over e squared, right? And then as we take this green one, here we should first have 2e squared on h conductance, because we have a doubly degenerate band there, right? And then it should go down to 1. Wait. Sorry. It should go up to 3, because we have both of these plus this. So here we go from 0 to 2, right? And here we go from 2 to 3. Does that make sense? Because we have 3 bands that we...
So on the very left, there are more layers, and on the very right, there are less layers.
Well, it depends. Okay, so this is doubly degenerate, and then it's split here, and then it's doubly degenerate again here. It's split there. Does that make sense? So if you measure conductance, as you go from, this is just delta G, but you should go from, and in this one you go from, 2 to 1, and so it goes from high conductance to low conductance. And this one goes from 2 to 3, so you should go from low conductance to high conductance. And so if you just measure delta G, in that case, you should alternate between the phase of your oscillations. Okay? And then that's the sign that you're sweeping through multiple subbands. And your overall conductance scale should also increase, which it does, but in that, the image I showed you is a little bit artificially separated. Yeah. Okay. So our theory collaborator Matthew Gilbert did some simulations of this and showed that indeed that we even though we don't actually have 0 conductance where you think there should be 0 conductance, but that may be associated with a little bit of tunneling or co-tunneling across the contacts due to band bending. But overall, there's a good fit between theory and experiment. And again, so how do you characterize these surface states? Well, you can show that indeed at least you get something that's consistent with theoretical expectations, that you do have evidence of 1D mode manipulation, and that you wouldn't get any signatures at all if you didn't have surface states and coherent 3D transport. Okay, so now we can show that at least these basic qualities of the topological materials are there and are reasonable, and you can measure them in transport. Okay, so now you can say, okay, what sort of devices can you make out of this? I started with an FET device because everyone wants to make a transistor out of it. And again, when we write grants, we always say maybe this switch can be used as a transistor if we move from this state to the other. So, here's a question of, how good are topological surface states as transistors? I mean, the fact that you don't see them in industry that doesn't mean anything. It's really hard to beat CMOS. But, the benefits could be that you have no impurity scattering, that you get these dissipationless channels down to small scales. So if you just took a really simple configuration and tried to make an FET out of topological materials, what do you see? And you see curves that look like this. These are transfer curves in ECE people. And actually, this looks very similar to what you'd expect for a silicon transistor. It has sort of linear behavior, and then it saturates at high voltages. And you can also measure the mu as a function of voltage, and you can say that it's to first extent it looks like a transistor. The problem here is if you look more closely at the numbers, you can see that the saturation current is actually quite low, and the mobility is very low. The mobility is something like 20 times lower than you'd get for a silicon transistor. And this is actually it's a little disappointing because on the one hand, it seems like you have this dissipationless channel and you should get this really high conductance, which you do relative to the size of the thing. But I think as someone mentioned, you also don't have very many electrons. And so your mobility is killed by the fact that you just don't have many carriers in these systems. They're not metals, and they're not even like doped semiconductors. And so at the end of the day, even though you have a dissipationless channel, the mobility is just much, much lower, and you get this saturation at currents that are much lower than the currents you'd need to apply for real devices.
You just said that transfer is ballistic, but mobility is for diffusive transfer. How would you calculate this mobility?
Yeah, so I think I mentioned the transport was quasi-ballistic.
Oh.
You actually have phonon scattering in these.
Right, so the situation is disappointing.
Yeah, it is, and then that's a problem. So in theory, there's lack of backscattering, right? But unfortunately, when you have a real wire, there's side scattering and there's angle scattering. There's all sorts of other scattering that can happen that's not just backscattering. So even in those nanowires that I showed you, where you saw Aronoff-Bohm effect, it was quasi-ballistic. Maybe we saw Fabry-Perot oscillations. It was quasi-ballistic enough, at least on the 200 nanometer scale, that we could see those effects. But when you have a semiconductor with a reasonable channel length, you still get enough scattering that it kills the currents that you can carry, basically.
Let me correct that in bulk semiconductors, the saturation actually is due to optical. So once you get the optical photon frequency, you get saturation.
Yeah.
But here, energies are small. So
yeah. So this is it's a good question because I wasn't quite sure, but it's velocity saturation that's not from scattering. And well, okay. So in semiconductors, I think that the reason that you get this mobility saturation is that you actually deplete carriers in the FET, right? So you have a source and a drain, and if you apply a high enough voltage at the drain, you start depleting carriers that prevents you from having your channel actually flow anymore, right? Because you have to have a depletion region, and you start depleting that region underneath with a high enough voltage. So that's where the saturation comes from in semiconductors, not from optical phonons, but from that saturation of that. In this case, it is phonons that's actually limiting you, which is different from what happens in a semiconductor.
Actually, this notion that the backscattering is quenched,
Yeah.
it's not really valid. That's my opinion.
I agree. Yeah.
If you look at it very carefully,
Yeah.
it's scatter 90 degrees.
Yeah.
Because it's not an edge state.
Yeah.
So it's,
Yeah.
So yeah, I agree.
Yeah.
You always find very
Yeah.
disappointing.
Exactly. No, yeah.
But this is
Yeah.
a 1D or 1D channel. It's not a surface.
No, this is yeah. It's a nanowire, but it's still. there's enough of a surface that you can, I mean, scattering can happen on the length, and this could be 100 nanometers, right? It's not, by 1D, I don't think it's not 5 nanometers, it's like 100 or 200, right? And what Fawn was saying is exactly the point, is that we talk about, so we have to be careful. This is partly why I wanted to talk about these things, because when we talk about things like lack of backscattering, my mind immediately jumps to, okay, it's dissipationless, but that's not really true, right? There's other sorts there's every other scattering happens, just not directly backwards, but you can get side scattering, so you're still limited by that in these systems, and then you don't have so it's still better than, the scattering is still better than you get in a semiconductor, but then you don't have enough carriers to actually take advantage of that benefit. That's a problem. So it's neither truly ballistic, nor are you high current in these cases, so you're just killed in that in-between regime, unfortunately.
Sorry, and
Yeah.
photons are bulk almost.
I think
you
both.
don't care about momentum conservation, so they scatter.
That's the assumption here. Yeah. So this is low mobility due to the low density of states in these systems. But I do want to mention one thing, which is actually really kind of interesting, is that if you then assume that you have low currents and look at the energy, let's say you take an FET and you want to switch it on and off, and you look at the energy just with a gate. You just switch conductance on and off through the gap. You look at the energy it takes to do that switching and the delay time, right? So for a high performance field effect transistor, you want something that's down here, low energy and really fast switching, okay? And what you see here, what you see here are the highest performance CMOS transistors are really fast, but take quite a bit of energy. And then the highest performing topological transistors actually can go faster with lower energy, right? Again, this is for low current density, so these would have to be really special application transistors, but for these special application transistors which have low currents, they could potentially outperform CMOS. So even though these aren't going to ever be in your home computers, for very specialized applications, there may be some potential there. So there's some theoretical benefits to them. You could use things, these aren't using topological to non-topological switching, they're really just gating carrier density here. So you could use other sorts of switching, but overall, to improve these characteristics, you still need, better control of surface state quality, better control of where the Fermi energy is, and then there are some limits you can't overcome, which is the scattering in these systems, which is just going to happen. The other application I wanted to mention is interconnects, because this is something that I've been, whenever I show that little wire with the high conductance, I always say, this could be good for an interconnect, and then I just move on from there. And so I thought for you guys I'd actually show what an interconnect would look like in this case, because again, as you can see, this edge roughness and grain boundary scattering in copper makes them too resistive as they scale, so you can say are TIs any better for this? And the answer is yes and no. So again, you get this scattering and electron-phonon interactions, which if you look at mobility as a function of temperature, the mobility starts out pretty low, which is going to hurt you in terms of interconnects in general. But however, if you look at the resistance of topological nanowires as a function of size and compare it to pure copper, which is the gray line, then they're never better than copper. Okay? However, I didn't realize this until recently, but the interconnects in most chips aren't pure copper because copper diffuses into silicon. Did everyone know this, that they have liners around them? Who knew this already? Okay, I taught you something. You knew this, right? I know you're the only one. I don't know why I didn't know. Okay, so it turns out that they're not pure copper wires. They have a liner because copper diffuses. And so you have to put a liner around the interconnect, which then limits how small you can make it. And it limits the size that you can scale the copper down to. So if you had pure copper, it would beat everything. But copper plus a liner just doesn't scale very well at all. In fact, it scales terribly, as you can see. As you get to about 10 nanometers, the resistance just grows exponentially. So in this region, for nanowires at below about 10 nanometers, there's an opportunity for new materials like topological materials that could outperform interconnects. And interconnects on current chips use something like 50% of the power lost on chips is lost in the interconnects. That's a huge amount of power. So if you can find a way to have lower resistance interconnects, you could actually, as they get smaller, you could actually have huge energy benefits in this case.
On this point, Julie Charles she found a topological wire, but I forget what material it is.
Yeah.
That beats copper.
Oh, even here. Okay. Oh, really interesting. Okay. Yeah.
There's a patent for it.
Oh, okay. Okay. So
material.
So apparently this does better. I mean, as you can see, it's very close here anyway, right? They're not too far apart. But and anyway, this copper line doesn't matter because this isn't feasible for, right? This is just theoretical. But hers goes way below for topological materials. So it turns out there's an even better opportunity in this, right? There's materials that have such low resistance that, you know, my point at the end is going to be it's hard to beat CMOS, but you know, depending on how desperate we are, right? It's nice at least to know that in a realistic technological application, it has a real advantage, right? Not a, you know, we think this might work, but it has a real advantage over current technologies that, depending on what our needs are, is something that could be applied. Yeah.
I'm just curious, do you know what is the geometry here? I mean, of course, for the resistance of metals, it would be width and thickness of a via, but which dimension is width here?
The cross section, I'm assuming.
Yeah, but because...
I mean, I think these are nanowires, actually, so...
These are nanowires.
Yeah.
So this is not copper via, but it's a nanowire.
I believe these are copper nanowires and copper. Yeah, I don't think that this is... yeah, I think these are nanowires made of copper. And in fact, even for... I'm not sure that... I mean, this is compiled data, so I'm not sure they even took this data necessarily.
Same point, when you make your transistor,
Yeah.
do you protect this direct oxidation?
So I mean, they did. I think this is. I mean, they have it covered with it's hafnium oxide and then with a lead gate on top. So yeah. And then this is an old experiment. This is an old experiment. There have been experiments since then that have done, you know, graphene layer, you know, hexyl boron nitride layers, and they protected it pretty well. But I mean, even if you protect it, the characteristics here don't change very much because that's intrinsic. The characteristics here could change somewhat, right? Okay, now I see why everyone goes over. I've gone through like so few slides. That's fine. Okay, so okay, that's interconnect. I think that it's interesting that they have some use there. You know, I want to quickly mention a couple other potentials. One is you know, hybrid devices, quantum topological devices, superconducting topological devices. Just to mention this, I noticed that there's well, this isn't a Majorana conference, but there's no and I'm not going to talk about Majoranas, but if there is interest in looking at superconducting topological junctions, for example. You know, you have invariant bound states and maybe Majorana bound states. You don't have Majorana zero modes. For those, you need a trijunction in this case. But just a regular junction is something that's also been interesting for people to look at. Here we go. You know, these are lateral STIS junctions they're not everyone's favorite Majorana system because it's 2D. It's complicated. You can't get a Majorana zero mode out of a 2D junction in this case. There's lots of surfaces, there's conducting bulk states, but because it is a 2D system, if you could etch out trijunctions and different ways of manipulating, it's possible that you could find more ways of performing logic in this than you could, say, in a nanowire. Trying to decide in real time how much to talk about. That's fine. I'll just keep going. So the other thing that we've done is looked at surface states. So you might ask, in this case, if you have a topological system, what do the superconducting surface states look like? And here we have, again, another flake, the same picture, but it's a flake that looks like this with aluminum leads on it that make a very narrow junction to see if there's unique surface state properties in the superconducting regime. In this case, you can see, you know, clear gate tunable surface states, not surface states, gate tunable supercurrents in this case, which is expected for these sort of systems, but you can couple it very well. You know, again, we can tune the supercurrents through the Dirac point and see how they behave. If you get differences in the supercurrent near the Dirac point, as opposed to where we believe around the bottom of the bulk conduction band. And what we find by comparing this data, and this data is current, this is differential conductance, and so this bright blue line is the derivative of the conductance, which shows you where the critical current is. So this blue map tells you what the critical current looks like as a function of gate voltage as you go through the bottom of the conduction band and then the Dirac point. And actually, when we took this data, I was kind of hoping to see some big change happen as you went through the bottom of the conduction band. As you see from the data, almost nothing happens. But it turns out that that's okay, because when we compare this to simulations, what we see is that basically the surface states are carrying all the supercurrent, even when you have bulk states available. And so this is one of the things that makes coupling topological insulators to superconductor is really interesting, that even if your Fermi level isn't at the Dirac point and you couple it to a superconductor, your supercurrent still mainly flows through the surface states. And so you can get surface state conductance even when you don't tune into the Dirac point. In this case, okay, are there Majorana modes? I said I wasn't going to talk about it, but I will just say it's complicated. There's data showing missteps in your AC in Josephson junctions, some evidence of 4-pi periodicity, some evidence of weird Aronoff-Bohm. I'll say a little bit more about Aronoff-Bohm. But we recently published a little paper that we just took a topological insulator, Josephson junction, and it had a step function in it. So basically, it was a film of Ti, and it had a thickness step. And what you can show from the thickness step is the simulation, is that just from one step in the thickness alone, you can get all the asymmetries that people have seen before that they associate with Majorana modes. You can get lifted nodes, you can get asymmetries in the case. And so it turns out for most of these measurements, it's really difficult to distinguish between disorder-induced anomalous behavior and Majorana-induced anomalous behavior. And I think that's a controversy that just hasn't really been solved yet. But I will say that there's, people are still coming out with papers on how to look at qubits with topological insulators. This came out just last year. This is, again, a way of looking at a nanowire of topological insulator, so without a large external field, and looking at Majorana bound states in these sort of nanowires. The idea is that these systems have overall less disorder than the semiconducting nanowires, and they have intrinsically less disorder than the semiconducting nanowires. And so if it is indeed, as much disorder as they have, if it is indeed disorder that's preventing us from seeing Majorana zero modes or bound states, then it's more possible intrinsically to see it in this sort of system. And then people are just kind of giving up on the topological properties altogether and just making them in regular qubit junctions, transmon configurations, and then see what happens in there. So I don't know what the advantage of that is, but they're doing it, and there it is. So there's lots of ways that you can use these things that are not just looking at Majorana zero modes, but also I have to say that in all of these cases, you have to manipulate the 1D modes of topological materials, and we've shown that you can do that at least. So at least you can reach the conditions where you can manipulate 1D modes, where you can couple them to different materials, and at least create conditions where you could see these effects. Okay, time?
You can use a few more minutes because we are running so
late. Okay, I'll just a few more minutes. Okay, I'm going to end with one more set of experiments because they're fun. So that was all I was going to talk about, the electronic devices, and I'll summarize those at the end. But you can see that there's some promise for actual electronic devices. I think that for a lot of us, the excitement is not in the devices that we know, but in the devices that we don't know. And so you can ask now, what other sort of states can be induced in these systems? And there's a lot. You can couple them to magnetic materials. I'll talk about that. In this case, it turns out that a junction, a superconducting junction of topological material that has a magnetic field in two directions on it can induce a state that's similar to an FFLO type phase. That's interesting because you have this finite momentum Cooper pairs that can have very long-range pairing. And so basically, for most superconductors, as a function of magnetic field and temperature, you lose TC because of orbital effects. In this case, because you have this additional order through this FFLO phase, you can have a much more robust superconductivity up to much higher temperatures and fields. And also, there's even thoughts that this sort of momentum shifting in these systems could lead to superconducting diode effects, for example. So these sort of momentum shifted states have been seen in 2D topological materials. We were curious if we could see them in 3D topological insulators. To show this, I just want to start by mentioning that we're looking at Fraunhofer patterns here. Fraunhofer patterns are single slit patterns. Right? So it's very much like if you take a single slit in optics and you look at the resulting diffraction pattern. In this case, it's a single slit where you're looking at the diffraction of your supercurrent, effectively. So as a function of flux through the slit, you can either get a uniform current or something that looks like this. And so the critical current should have a form like that. Now, the reason this is interesting in topological materials is because of spin momentum locking. When you add an in-plane field, it shifts the momentum, okay, and therefore it shifts the corresponding Dirac cone and Fermi surfaces. And so you should actually get a shift of phase in this case. Here we go. So this should give us this additional phase that you get from shifting the Dirac cone, gives you additional phase to your center of mass momentum to your Cooper pairs. Okay? And therefore it adds this phase across the junction, which we call the Zeeman term. Okay? We should also see an Aronoff-Bohm term because we're putting a field in along the current wire. So we get a Zeeman term, an Aronoff-Bohm term, and the standard single slit diffraction term, and we can model the transport current in this case and see that we get simulated Fraunhofer patterns where the spectral weight is shifted to larger values of field in the case of this finite momentum shifted states. So when we measure this, what we see, this should lead to in conductance, in 2D conductance maps where blue is superconducting and yellow is these are all the colors you see are superconducting and red is normal state. You should see a trident pattern of the superconducting resistance, which is due as a function of out of plane field and in plane field. Okay, so be really quick. We measure this. That's junction. And we see something that looks like that. That's not quite what I showed you. It looks tilted, right? We should see something that looks like that. So what we do is we just tilt it back. The magic of PowerPoint. And when we do that, it looks really good. And so this is the data, and this is the simulation. And again, this is these are, what you see here are your Fraunhofer patterns. If you make a slice through here, you'll just see the expected Fraunhofer patterns of that single slit pattern. But now you can see the single slit pattern is lifted to higher values of BZ, basically in this trident shape, very much like what we expect. We can show that this tilt is just due to the shape of the junction, both due to the asymmetry of the leads because the shape of our bismuth solenoid and due to a flux focusing effect. Flux focusing is just if you apply an in-plane field, because of the Meissner effect of the leads, it basically creates a small component of out-of-plane field. And we apply a really strong in-plane field in a very small out-of-plane field. So a small amount of flux focusing leads to this sort of tilt in the data. But we can basically prove that we have the sort of patterns that we expect. We measure it for different thicknesses of samples because from the slope of the change in the slope we get here of the center of these nodes, it should tell us of the relative contributions of our Zeeman term and our Aronoff-Bohm term, and our Aronoff-Bohm term is related to the thickness. And we can show that we get that from, as a function of thickness, that the Zeeman contribution is important here. Okay, I'm going to end. We can simulate a bunch of different ones. It was cool. It's fun. But the conclusion here is that you can still see interesting sorts of behaviors beyond emergent behaviors here that, if FFLO states are ever useful for anything or emergent quantum states are useful for anything, those are still evident even in 3D topological materials. So I just want to conclude today by saying that overall, I would say that there's probably not immediate application in conventional computing elements like things like interconnect or Joseon devices, but, there's special applications like low current devices and also a lot of interesting new emergent states that can still be studied. It's really hard to displace CMOS. And so I don't think that should be this alone shouldn't determine whether something's useful or worth studying, right? If it has some potential and it's interesting, it's still worth studying because, CMOS is just here to stay for a long time unless there's something really unique about the material. And then, as Fawn said, you patent it and see where it goes. You still need to have advances in these materials like having less disorder, increasing gap energies, showing properties at high temperatures is an issue still, and also some simple measurements that are relevant to topology. But overall, there's some promise, but it's limited. I think there's still a lot of potential in topological spintronics, topological materials coupled to magnetic materials, and that will be the topic of my talk tomorrow. So thank you very much.